Okay, so theory with experiment, calculations we're about to do now, and this is your experiment. So let me just do a couple of shots at two different angles. So I'm just going to choose, for example, I'm going to shoot this guy at 25 degrees here. Now note that in this particular part of the project, that the maximum height or the vertical height must be 0. And I'll be going back over that once I show you the questions you need to answer. So let's see, we have this guy at 25 degrees. You can do it yourself just to play around. You should have it in front of you, and you shoot the pumpkin. Okay, splat. Now notice something if I do the complementary angle. I'm gonna do that at 65, and you should do the same thing. What do you notice about the horizontal distance for 25 degrees and 65 degrees, the complementary angles?
They had the same displacement.
Yeah, the same horizontal displacement. And of course, this is a physics project or physics engine that utilizes the actual physics that we're going to see. So we're going to prove why that if you have a projectile shot at two angles, the complementary angles, where the maximum height is equal to 0, that you're going to get the same horizontal distance. So we can track that here. You can take this guy, pull him down. If you have this on your screen, you should just pull it from over here, and just triangulate this this dial on top. You can see that the horizontal distance, or the range as we call it, is 25.3 for both essentially. Okay, we can just take that off and just verify that. So here's pumpkin at 65. He's at 25.3. You can see that, and you can zoom in if you, well, sometimes it won't. I wish there was a scroll bar, but sometimes you can zoom in just to get a better look. That's 25.3, and I'm gonna do the complementary. 25. So you're utilizing physics and geometry. It's all gonna be always related. So 25 degrees. So we get the same range, 25.3 at 25 and at 65. So there's a reason for that. Well, they built this little game, this little simulation off of the physics that we're going to see. Okay. So, but before I do that, notice something. I can play around with this. Play around with the diameter. What if I change the mass? I just go from 1 kilogram to whatever, 834. Nothing changes. Seemingly 25.3, and let's go to 65. Same deal. And we're going to see why the mass doesn't matter. But would the gravity matter? Oof. So that's at 65. Yeah, it should make some kind of sense. Well, we'll see why that the range is shorter when the gravity is increased. And at 25. We're going to get the same range, but it's going to be a shorter range when the gravity is increased here. So 17.53 for both of those. Let's do it again. 17.53. And 17.53. Gravity increase. What about if we decrease it? What do you think is going to happen if I decrease the gravity? Anyone out there?
If you decrease the gravity, maybe it would travel further. Maybe I'm not
Okay,
sure.
let's see. We always have hypothesize, we speculate, we put our best guess forward, and then we go test it, right? Hypothesis to experiment. Oof. Oh my goodness. Almost off the screen. You're correct, Miles. Can't even get over there. Anyway, we can calculate that once we get there. So let's go to 25. And oof. So same range, but now with gravity decreased, it travels further. And let's see why that works. So I'm gonna erase this guy. And again, Statue of David is, you know, mocking us standing so close there. All right. Okay. So we've changed the mass, see what happens. Nothing, diameter, nothing, gravity. Yes, definitely. And let's look at the physics equation that governs this action. This is what we call this equation here, a horizontal range equation. We call it R. Same as delta X, but we just call it something physical. Hey, that's how far you, this is the range, shooting range, go out in the middle of the desert, shoot some rockets, life-size rockets, calculate your distance for the range. Okay, I'm not going to bother you with the pesky derivation. I'm just going to give this right to you. And I'll say this is VI squared sine 2 theta, double angle formula. Some of you may recall that from your integrated math, your trig, but or not. But again, trigonometry, the stuff, those trigonometric equations that you use, very powerful in physics. With certain things, you're not necessarily going to use all of those trig equations, but there are situations where you could. All right. So if we go back, if we recall, so like I said, horizontal range is R. VI is our initial velocity. Recall that. And that was 18. We're going to keep everything at 18 meters per second for the horizontal and the vertical stuff. The theta is the angle. We had two angles. This is a double angle formula. This is the physics, the math equation that governs the physics of why at two complementary angles, you're going to get the same R. Keeping V constant and G constant, right? If you change one of those variables, then, everything else changes. So in a good experiment, you want to change one variable at a time. In this case, we're going to be changing the angle theta, changing it from 25 to 65, or 35, 55, or 70, 20. We're only going to be changing theta to produce these R's. R is going to be dependent on theta. We keep VI and G constant because we don't want to be changing all the variables. Then what kind of experiment do we have? We have a very skewed experiment. A lot of skewed the results that we can't evaluate. Just doesn't mean anything. And theta is going to be an angle, so it's going to be complementary angles. You should know that from geometry. Two angles that add up to 90 degrees, And G will always be 9.8. Well, you can mess around when you get to your breakouts and all that stuff. You mess around with G, different projectiles, shoot a piano, shoot a human being, shoot a car, whatever you want. I'm going to keep it at 9.81. Because that's our gravitational field strength at the Earth, 9.81 meters per second squared. You can mess around and see what it would be like on Mars. I think the gravity is 3.7 meters per second squared, allegedly, around there. And then on the moon, 1.6 meters per second squared, and so on. You know, Jupiter is 25 times the Earth. We calculate that just to verify that, but it's definitely larger than here. So it's I don't get the number 25, 25 times larger, 25 times gravity, but we can definitely calculate that and know that gravity at Jupiter, Saturn, the gas giants, is larger than here. Okay, so let's so we had 65 and 25, right? So for example, when you do your lab, you're going to get your own complementary angles. You can do 65, 25. You can, use this data I'm about to show you, 70, 20, or whatever the case is. But try to make those complementary angles such that, you can see where things land. If it goes off screen, you can't track it, because that's going to be important to verifying your results. So you're going to calculate your stuff, and then you're going to verify with the screenshot. So it's going to have calculation screenshot for 5 pairs of complementary angles. And that will be explained in the document coming up. So for example, we had our equation above. And so we had 18 squared, and then sine 2 times 25, right? Because that's angle theta, 2, the double angle, 2 times 25 over 9.81. Now, do that calculation yourself to make sure that you can get 25.3, but so it's basically sine of 50, right? Sine 50, and that's going to be 0.66, 0.766. Divided by 9.81. So the numerator is going to be 248.18 divided by 9.81. So 25.299, 25.3, and that's what we got. What we saw. So this result helps the engineers, software engineers there, to create that simulation, because this is the mathematics behind it, right? 25.3 meters for the horizontal range. So at the complement, well, we can say range at 25, whatever. Range at 65, as we saw on the screen, it should be the same. So 18 squared times sine of 65 times 2, 130, right? .766 times 18 squared, 248.18 divided by 9.81, 25.3. You should see that. Are there any questions thus far? So 18 squared multiplied by 0.766 divided by 9.81 gives me 25.3. So you can see right now that complementary angles yield the same horizontal range, R. And so what you're going to do, you can take this as one of your 5, and then you do the other 4. So, you just come up with any complementary angles. Make sure that your projectile is going to stay on the same screen, because you can get complementary angles where the stuff is off screen. But try not to do that. Play around with it. So now, this is our example calculation. So, okay, so that's the first example. This is the horizontal range. So this is the document I'm going to put on the Google Classroom. So this is what you're going to do as soon as you go to your breakouts and your projects here. So you're going to find the range R for 5 pairs of complementary angles. We already did 1 pair. You can do the other 4 are your own. The vertical height needs to be 0, h equals 0. So as we saw here, h equals 0. There's no height here. And we're going to do this for the next part. So this is our the first part. H is equal to 0. So next to these calculations, you need to provide screenshots verifying the range you calculated for all pairs of complementary angles. So you have your calculations on paper. Next to it, you're going to verify that result by a screenshot. So we shoot this again. Okay, that was pretty far, obviously. Oh, I changed my gravity back. Oop, 9.81. Okay, so and make sure that this, the dot lights up there, 25.3, and then 65. Do the same thing. 25.3. So this is a verification of your theory. You've theoretically calculated. This is our experiment. And you do that for all 5 of these. So then there's some other questions. What happens to the range R when gravity increases? We already saw that. What happens to it decreases? Does mass or diameter change the range? Why? Look at the equation. So we've already verified that, what those answers are. So now let's get to the next part, the vertical height project. All right. So in this particular part, we're going to calculate the height between the cannon level and the apex of the projectile. I'll show you what that means here in a second. We're going to add this height to the initial height to obtain the total height above the ground. Come clear in a moment. Next to these calculations, provide a screenshot for the experimental maximum height you just calculated. As in the HRP, horizontal range project above, provide these solutions on the same separate document. After you get all of your maximum heights and your times, the time will be given. You don't have to calculate the time. You're going to make a data table of each max height versus time. Determine if the data is linear or nonlinear. You should know how to do that by now. If there's any questions, please let me know. Then you're going to graph max height delta H versus time. Again, the same questions. What happens to the max height when gravity increases or decreases? Does the mass or diameter change the maximum height? Why? Look at the equation. Anyway, those questions will be subsidiary once we get everything else. Okay, so let's go back to the project. So I'm going to raise this guy up. So this is going to be our angular projectile motion project in terms of the vertical height. So let me just do an example at, say, 5 meters, and say like that 26. Yeah, arbitrary angle. So what we're going to do is we're going to take this original height. We can call this y initial, and then what we're going to do is we're going to calculate the maximum height above the level. So let's show what that means. So the maximum height above the level, okay, the total amount of height is 8.17. So between 5 meters and here is the maximum height of 3.17. That's what I mean by adding it to the initial height. So the initial height is 5. The final height, if you will, is 3.17. So the total height above the ground is going to be 8.17. And they give you the time already, so you don't have to calculate the time. There's a way to calculate it, but you don't have to. So you're going to take the height that you calculated. You need to calculate your heights. You just can't show me the screenshots, but you need to calculate your heights and use the times given and flood a data table. Then graph that information, then answer those questions at the end. So let's take a look at how to deal with that. Okay, so then our vertical height project. Yeah. We're going to be using this equation, delta H. It's just basically delta Y, but height. You know, we're saying the word height, we'll just use a variable for it. H, VI squared sine squared theta divided by 2G. So this is going to be the equation that you're going to use to find your height between the cannon level and the apex. So for example, if I have my initial velocity is going to be 18 again. It's going to be 18 everywhere, 18 squared. So sine squared theta, when we do a sine squared, that's just going to be the same thing as sine of, let's say, I'm going to use angle 20, right? Let's see, and I'll demonstrate this. Sine 20 squared divided by 2 times 9.81. And so when we do this, you should do this yourself. You're going to get, whatever you're going to get. Sine 20, and then we square that. So this is going to be 18 squared times 0.1169, you know, 3 or 4 places here, 19.6. Divided by 19.6. That's going to be equal to 1.93. And you say to yourself, okay, well, that's my maximum height, and go on to the next one. Nope, that would be your height between the starting point of the cannon at a particular height up to the apex. Let's show what I mean by that. Let's go all the way to 14 meters, for example. I'm going to do 15. So I would say start at 15, come down 14, 13. Start at 15 and come all the way down to 1. So I'm going to just arbitrarily do 14 because that's what I did last night. Okay, so at 14 meters, 20 degrees. Let's see if our 1.93 is accurate. Okay, there goes the pumpkin. All right, so here we see 15.93 is our maximum height from the ground. Our initial height was 14. We calculated 1.93. So 14 plus 1.93 is 15.93. Verified result. All right. Any questions on that thus far? If there's any questions at any point, you know, please stop me.
I have just a quick question, Mr. Kelly.
Yes.
So the height is 15.93, and then you're starting rate at 14 meters in the simulation. So then and you want us to calculate it going down, but wouldn't the answer be the same every time? Or do you want us to change the degrees of the cannon? So
oh boy. All right. Let's do this equation here. So, okay, the total height that you should be reporting here is going to be the initial height plus the calculated height that we just got, the 1.93. Okay, so this is going to be 14 meters plus 1.93 makes it 15.93 meters. It won't be the same, the heights and everything. It's going to shift, you know. It's not, you're going to get different numbers each time. Just to quickly answer your question there. So this will be our first data point, or maybe the second, because the first one should be 15 plus whatever your angle is. So this is what I'd like you to do. So you can start at 15. We already got 14. We start at 15 and 15 degrees. And for each 1 meter down, you want to increase the angle by 5 degrees. 15 at 15, 14 meters at 20, 13 at 25, so on and so forth. Questions there? We start at 15 and 15 degrees. Okay, as we can see here, our maximum height from the ground, 16.11. That means that when you calculate this, this height from this starting point, this reference level, that the height between this reference level and this dot is 1.11. 15 plus 1.11 is 16.11 from the ground. This is the initial height, and this is your final height. Then you're going to go to 14 and 20. Okay. And then continue on down, 13 and 25. And so forth, 12 and 30, and keep on going down by degrees of 5. Hopefully that ensures that your range can be seen on the screen. Pretty sure it should. Does that answer your question, Miles?
Yes, I didn't know we were adjusting the angle of the cannon. So then I was just
Yes, of course, yeah. Where the angle between this reference point and the midpoint of the cannon, yeah. So that's our first point, and then that, well, technically our second, because 15 will be the first guy. So again, it's going to be this delta H equation, height, which is VI squared sine squared theta over 2G. And we do that for all the heights and all those angles. So our first data point will be 15 meters at 15 degrees. You are going to get a range. You're going to calculate that. So that first range here, or the first height, 1.11. We add that to 15, we got the 16.11 as we saw. So you're going to take that 16.11 and you're going to put it into a data table that looks like this. Height versus time. They give you the time already. So you're going to do 16.11 meters time. And the time is given there. Oh, that's a little bit, 0.47. And you just flood it for all of these heights. You're going to do, it's going to be 15 heights 15 times. Right? And then determine if it's linear or nonlinear, graph the data, answer those questions at the end. So, okay, I've talked enough. Let's get on out to breakout room.